All right, I guess I'll get started. Yeah, so remember last time we were looking at this main analytic theorem, which was if X is a closed and connected Riemann surface, and rho was a smooth two-form, so real two-form on X, then there exists a smooth U with Laplacian U is equal to rho if and only if the integral of rho over X is equal to 0, and this U is unique up to constants. Okay, so last time, right, I tried to convince you that we could get the existence of such a U, at least in a kind of abstract sense. So in some kind of Hilbert space. So the idea is last time, right, we showed that right, if we started with a sort of space of functions, or not really a space of functions, but just an abstract vector space, which we were supposed to think of as sort of the space of functions whose integral was 0, so that of course requires a choice, which we're not making, and we let H just be the completion of H0 with respect to the inner product given by the Dirichlet energy. Then what we showed was that there exists a U in H such that for all psi in H, if we took we defined an operator rho hat of psi, which was essentially the integral of X of the form rho against psi, that was equal to the psi paired with U, with the Dirichlet energy. And this was all just an abstract theorem, so now we want to turn this into something more concrete so that we can actually apply some regularity theorem to deduce that U is not just in H, but actually is in H0, and so is really a smooth function modulo constants, which is exactly what we want. Okay? So I sort of, I think I kind of made a hash of this the last time. So let me just explain exactly what I mean by this. Right. So the idea is that if we, in some sense, if U is in H0, it would be represented by a smooth function. But we're taking this completion of H of smooth functions, so U is no longer represented by a smooth function under this equivalence relation. So what we want to do is say that it's really represented by some other class of functions that we can understand concretely, again, when we take the quotient. So the way to do that, maybe a little more explicitly, is to say, right, so U being in H means that there exists a sequence of UIs in H0 so that the UIs converge to U in this in the norm of the Hilbert space. So these guys. What we want to say is that there exists phi in now smooth functions of X, so that if we take the class of phi equal to UI, then we can pick then the claim. So we can pick the phi such that phi converge locally in L2 to some phi, which is an element that's locally in L2 on the space X. And so then the idea is supposed to be that U is supposed to be, the class of phi is supposed to be U. So this is just an intuition. Right, so the reason there's something to check here is, of course, all we know about the phi's is that their Dirichlet norm is, we know something about their Dirichlet norm from this kind of identity, right? So it's related to their L2 norm. But I mean, we need to make a choice of the constant, and if we make a bad choice, there's no reason that we can get this local convergence, right? So the proposition, so one way to get around this, of course, would be to, say, introduce a volume form on X and then prove that with respect to this volume form, we had some kind of Poincare inequality. That would be a way, because then we could pick the phi's to have integral 0 and use this Poincare inequality to get some kind of L2 control. That has some problems when you try and do it. I mean, first of all, you have to make choices, which one wants to avoid, and it's a little bit, in the non-compact setting, which I'll just state but won't get into it, it has some problems. So maybe I'll just give the idea, I'll give the statement, and then I'll give the idea of the proof. So the proposition, which one sort of formalizes what I just said there, is that there exist phi in C infinity of X with ui phi equal to ui, and so that the phi converge in L2 loc of X to a phi inside of L2 loc of X. So what this means is just to say that in a chart which is bounded, right, the phi's converge in L2 to something, to phi, basically. The idea, I mean, you have to check something, but the idea is that L2 loc makes sense on a manifold. You just check in a chart where the image of the chart is a bounded set, and you see that it makes perfect sense to talk about L2 functions there in the image, and then you just have to check that the space of L2 functions in the chart is if you pull back, if you look in a different chart, that you can kind of identify all the spaces. So it gives you a well-defined notion on the manifold, and the convergence makes sense. So again, the convergence just means to check in a chart that you have convergence, and you have to prove that that doesn't depend on your choices. Of course, it's much simpler if you just pick a volume form and then use the volume form, but you don't have to use a volume form if you don't want to. It's a notion that's independent of the choice. But then the upshot of all of this is if we go back to what this means, right, this phi is supposed to represent U, and so then we sort of interpret this identity star. So the implication of this is then that the implication that now phi is this genuine function that's locally in L2, and the implication is that if you integrate over X of psi against rho, that's equal to the integral over X of the Laplacian of psi times phi. Right, so this is an L2 function, so this makes sense. This integration makes sense, and so then this is true for all psi, say, in smooth functions on X. Okay, so that's supposed to come from this guy plus star. Okay, so to just give a kind of proof of this, right, just a general idea, right, so let's look at our surface X. I don't want to get too involved in it, but here's X, and we pick a point P, and let's just pick a chart around P, and let's pick another chart. So these are two coordinate charts, U and V, right? So the idea is, with respect to, we can pick, like, in the chart U, we can use the sort of Euclidean Poincare inequality to pick, say, the phi I. Right, so we pick phi I globally on X, but then we are free to add a constant to them, right? And so the point is we choose the constant to add by looking in the chart U and making sure the integral is 0 in the chart. Because then by the Poincare inequality in the Euclidean space, since we can control the Dirichlet energy of the UI, which in turn implies that we control the Dirichlet energy of the phi, that means that we can get L2 control, and we can pass to an L2 subsequence by, say, the Relic theorem. So that tells us that these guys actually converge. But sorry, we don't even need to use, I mean, we really have L2 control, so we get an L2 Cauchy sequence from the fact that it's a convergent in the energy. So then the point is we can choose the phi's. These are in U, right? But we can do the same thing. If we do the same thing, in V, then we get some different choices of constants, right? So we get psi I prime. And so the point is the psi I minus the psi I prime are just constants Ci, right? These are constants. Since we had to choose them differently depending on the chart. But so the observation is that these guys converge in L2, and there's an open overlap, right? And if they converge in L2 on one and converge in L2 on the other, then on the overlap, since that has positive measure, that means that they can't differ by something that goes to infinity. So that tells you that actually these differences remain bounded. And so the point is, I mean, if you read through what this really says, is that actually, if instead of choosing the psi I primes, you change the constants so that the psi I primes agreed with the psi I. So now you don't know that their integral is 0 in this chart. But the point is you still, because you've only changed by a finite shift, you'll still converge in L2. And so that means that actually, once you fix the choice of psi i's by this chart, you get a nice convergence in this chart. And then you can do a kind of open and closed argument to prove that because your manifold is connected, that you get a consistent choice on the whole manifold. Okay, so the point is that's the sketch of the proof. And so the upshot is, as I said, we get this identity over here. And so then the point is we want to try and use this identity to prove, we want to now to show that U is actually a smooth function. Not U, phi is now a smooth function of X. Okay. In other words, if we have an locally L2 function that satisfies this sort of identity, in other words, its distributional Laplacian is smooth, then we want to conclude that it itself is smooth. And again, right, you should convince yourself, but we can just work in charts, right? So it's enough to work in charts. Because again, being smooth is a local property, so you check smoothness of a function by just looking at it in a chart anyway, right? So that's to say we can reduce it to the following proposition, which is the local version of sort of a local version. Okay, so that if omega is an open subset, and that's just to say it's bounded for simplicity, subset of R2 and rho a smooth, say, 2 form, but really we'll just think of it as a function and use the Lebesgue volume form on R2, but I'll just state it this way. On omega with a compact support, and if phi is a L2 function, an L2 of omega, so that's why the bounded comes in, so we don't have to put this loc, such that for all psi in C infinity of compact support of omega, we have exactly this identity. So the integral of x rho psi is equal to the integral of x Laplacian psi phi. Then this implies, in fact, phi is C infinity, and it satisfies Laplacian phi is rho, sort of classically. Okay, so, and of course, so to convince yourself that we can reduce from this case to this case, it's pretty clear we check in a chart. There's only one thing we need to be careful about. So we're assuming here that rho has compact support, right? So of course, we're not assuming rho has compact support in the chart, because that's not that we can't ensure that. But remember, we had this trick where we were able to use the fact that the manifold was connected to sort of write rho as the sum of forms that were compactly supported in each chart, right? So we actually, that allows us to reduce to this proposition. Okay, so now let's prove the proposition. So proof proposition. So the first step, and this is essentially an exercise, I think, from yesterday. But the first step is to reduce to the case reduce to the case that rho is identically 0. Okay. So in the case that rho is identically 0, this is known as this is Weil's. I'm spelling this right. This is sometimes called Weil's lemma, right? And the idea is to just right. I mean, the point is that I mean, maybe not the point, but it's an exercise. As I said, is you can explicitly using whatever your favorite method of solving linear PDEs is. So, for example, looking at the kernel or using the Fourier transform, you can explicitly find a C infinite function, say phi hat, with Laplacian phi hat is equal to rho. Okay. Notice that phi hat need not have okay. So for example, use the Fourier transform, or as I think on the exercise sheet I had you do this using the fundamental solution. So this is explicit, and so then the point is, we're trying to prove that. You might ask why we couldn't do this in the first place, but of course the problem is about issues with the support and patching everything together. But the point is now, if we look at phi minus phi hat, which we'll just call this phi now as now satisfies Laplacian phi is equal to 0 weakly. And the point is, because omega is bounded, we haven't changed that we're in L2. So we've reduced the problem to this simpler problem, modulo proving there exists such a solution. Okay, so now we want to try and give an idea of the proof of this sort of Weil's lemma. Okay. And the key fact that we'll use, so the key kind of fact we're going to use is that if we smooth out phi cleverly, in a clever manner, then we get a well, one, we get a harmonic function. And then we can use properties of smooth harmonic functions to see that, in fact, the smoothing, if we do this cleverly, the smoothing, and then this part gives you that the smoothing is sort of is in a sense is unique, as we'll see what that means in a second. And what that tells you is, since we're smoothing something out, which means that it should limit back to what we wanted. If the smoothing always gives us the same thing, then the limiting back should tell us that in the limit we get what we smoothed out to be, so that the thing we started with was smooth to begin with. Right. So what is the key property of smooth harmonic functions, which we're going to use? So we're going to use the fact that if you have a Laplacian of a function f is equal to 0 on, say, the R disk, then we have the mean value property. So we have the mean value property. Right. So you should think of this as this is a differential equation. So this involves two derivatives of the function, but this mean value property is going to be something that's a kind of C0 property, or even lower regularity, in that it doesn't. It is C0. So what we're going to see is that the value of f at the origin is the same as the average over the disk of R, integral of the dr of f dA, or equivalently, it's the average over the boundary dr of the integral. So we're actually going to use this identity, as we'll see. So the point is, this is and an exercise is maybe to prove this. So exercise is to show this. But again, notice that unlike this, which involves two derivatives of f, this involves no derivatives of f. So it's and it's a classical fact, but which essentially is, I mean, in a sense, we'll be using this to a certain extent, but we won't state it explicitly. Is sort of any function that satisfies this mean value property, which is a C0 property, actually is you should check it satisfies this equation distributionally, and hence is really actually, by Weil's lemma, a smooth harmonic function. I mean, this is a very common theme, and it's definitely very powerful. I guess I'll leave that. Okay, so let's actually verify how we're going to smooth things. So how do we do the smoothing? So how do we smooth? Okay, so the basic idea is to do mollify with a smooth bump function, right? So we're going to consider this a smooth function eta on the unit disk on D1, such that one, let's assume eta is, this isn't so important, but might as well assume it. So eta is non-negative. 2, the support of eta is a subset of D1. Crucially for us, the integral, well, this isn't so crucial, but it's crucial, but that the integral is 1, and then the crucial thing in the application is that eta is radial, i.e., that is to say, eta of x is really just a function. Eta of a point z is really, it just depends on its radius. Okay, so it's rotationally symmetric. So you should convince yourself this exists, but that's a standard. Using cutoffs. So the point is, then we take these n epsilons, which are just going to be where we sort of rescale, and what you should convince yourself is, of course, this is clearly preserved by these rescalings. The support now of this guy is shrunk, so the support of the eta epsilon is now a subset of the epsilon disk. And then, however, we've chosen the scalings correctly, so that the integral is still preserved. So this is preserved, and obviously the rotational symmetry is preserved. So the point is, one way of thinking about this is that this converges in the sense of measures to the Dirac mass at 0. Okay, that's one of. And then the point is, we're going to use this to sort of smooth out the function, what do we call it, phi, by essentially taking some kind of weighted average. So this is the notion of a convolution, right? So we define now phi epsilon. So let me just actually, so just before I do that, so notice that notice we can extend phi to the whole complex, the whole plane by 0, and then we get a function phi that is in L2 of R2. Okay. However, some care is here. So do you think this guy satisfies the? Is this guy weakly harmonic on the whole of R2? So the answer is no, right? So you definitely if you tried to integrate by parts, if this was like a reasonable function, then you would see you'd get terms from the boundary of omega. So we've extended it for technical reasons, but we're only going to focus on it inside of omega. So that's something to. This guy is not harmonic in any sense on R2. Even though it's obviously 0 away from omega, so definitely harmonic there. Don't. Okay, well, maybe I should keep this. Okay, so let's see how this works. So now we want to do the smoothing. So now we smooth out the phi by taking phi epsilon is now going to be, by definition, the value at a point x is going to be, by definition, the convolution of phi with this bump function eta epsilon. And this is by definition, if you haven't seen this before, but it's R2 of, it doesn't matter, so this is eta epsilon of x minus y, phi of y, dy, or equivalently, and you should prove this. This is a proof, like check, it's an exercise, though it's a simple one. In other words, this would be sort of if you reverse the order of the convolution. So what this really says is that convolution is commutative. So then the point about this is that we've taken this, what you should think of this as you're shifting, this way makes it a little bit, well, either way, maybe this one makes it clearer. What you're doing is you're taking a copy of phi and then you're shifting it around and taking a kind of weighted average, which, if you think about something getting blurry, that should smooth things out. I think there's a very good short story by Isaac Babel called Lines and Color, which makes that clear. But that's an aside. So we smooth it out. So then you check, of course, that phi epsilon is smooth. And the idea is, in this point of view, is you have to convince yourself of this, but essentially any derivative in x, you can differentiate under the integral sign, and it should hit this guy. So so that should smooth everything out. You have to justify it, but that's not too hard. The other thing you have to justify is that phi epsilon is in L2. And then the final thing you should justify is that phi epsilon recovers phi in L2. So in other words, you really are kind of smoothing out phi, and you're going back to phi in this L2 sense. Okay, so that's the those are the main properties that I'll leave to you. And then the fact that's sort of, again, is something you should check, but is not too bad, is, I mean, you have this phi, which is sort of harmonic. So if this was genuinely harmonic, you were kind of taking these weighted sums of harmonic functions. You might expect it to be harmonic just by the fact that the Laplacian is linear. And in fact, if you just use this weakly harmonic, you can see that that's still true, except for you have to take a little bit of care because, right, as I said, phi is not harmonic at the boundary of omega. And so any kind of, whenever the boundary of omega shows up in this weighted sum, you would destroy the fact that the function is harmonic. So again, another property which you should check is that Laplacian phi epsilon is equal to 0. This is strongly, because it's smooth, on which is just the omega minus the tubular neighborhood of the boundary of omega. Right? So you have omega, and you have to delete epsilon, and then you have omega epsilon. And then inside of omega epsilon, you have a smooth function. So again, this is something you should check. Okay, so now this is a smooth harmonic function. So in particular, right, it has this mean value property. So then the final part of the proof, which again I'm not going to check. Well, maybe I think it's a good exercise. Is to see how to use this particular property here. Sorry, this should be DL. This property here to prove that the following fact is true. So that for say two positive epsilon prime and epsilon, then on omega 2 epsilon, we have that the what is it? I want to say that the if we try and smooth out epsilon again, phi epsilon again, we actually don't do anything. So the idea is on phi epsilon that we have the convolution of epsilon with eta epsilon prime is actually the same as taking the convolution of epsilon. Okay, but that it's also the same as taking phi epsilon prime convolved with eta epsilon, right? Which is by a symmetry argument is also going to be phi epsilon prime. Okay. So here, these two identities, if you expand out, this is some kind of should follow from some kind of associativity and commutativity of taking convolution. So this is just a property of convolution, which you should check. But these two are going to use very strongly the fact that that the phi epsilon has a harmonic function, so it has this mean value property, and two, that we actually took a radial function. So you should work out the details. Just in the interest of time, I don't think I'll get to that. But the point is now we have a function. I mean, now we have the sequence which is converging in L2, but on any, say, fixed compact subset of omega, once we get far enough in epsilon, then the smoothing guys aren't changing, right? So, I mean, you should convince yourself. I mean, obviously this is L2 convergence, so I mean it's a little bit weaker than what you would want to make this statement precise. But I mean, it's not too hard to convince yourself that actually this L2 convergence and the fact that nothing's changing on a compact set means that actually, in a sense, phi is equal to phi epsilon on that compact set. I mean, phi is only, of course, phi is in L2, so you can change it on almost everywhere, on a measure zero set. So the point is you get something that agrees almost everywhere with phi. So phi epsilon essentially agrees almost everywhere with phi. But the point is then we don't care about phi away on a set of measure zero, so we conclude that actually phi is smooth, right? And of course, the point is phi is smooth, one has to be careful. Phi is smooth on a compact subset of omega, but we can exhaust omega by compact subsets. So in a sense, phi is smooth at every point of omega because we can draw a little ball around omega disjoint from the boundary, and that's eventually inside of some compact set, and so then we can use this to argue that phi is smooth. Of course, sort of there is interesting questions about how regular phi is up to the boundary, but we don't need that, and I don't want to get into it. Okay, so that's the proof of how one proves elliptic regularity for the Laplacian. So obviously, we used a lot of special properties, so this property is very, very special about harmonic functions. So one has to develop different techniques to handle more general operators, but that's not the purpose of this class. Okay. Okay, so now we have our theorem in the closed case, which we already used to construct lots of meromorphic functions on a closed Riemann surface. So now the goal is to at least state a variant of the theorem on non-closed Riemann surfaces and try and argue that we can use this to get the uniformization theorem. So let's now say if X is, let's drop the closedness assumption as a connected Riemann surface. And since we only get, let's be, I'm going to be a little careful here because I haven't thought, I think, let's just say it's, since this is what we use it for, is a simply connected. So it's a smooth two-form on X with a compact support. Then there exists a smooth U with then if the integral of rho over X is equal to 0, then this implies there exists a smooth U with Laplacian U equal to rho and U vanishing at infinity. Right, so remember, what this meant was, right, we took the one-point compactification of X, which is to say we introduced this point infinity, and then the neighborhoods of infinities were complements of compact sets. And what this means is basically we can extend U to this one-point compactification with a value 0 there and say that it's continuous, and it's equal to 0 at infinity. But of course, we don't expect this kind of equation to make sense at infinity, since infinity, in some settings, will not even be a point, if you want to think about it not just topologically. So I just want to make a remark. Right, I mean, I'm putting the simply connected thing here just because if X is simply connected, you can prove that it has one end. In other words, sort of at infinity, it kind of only looks like an annulus. And I think that certainly in Donaldson's notes he uses that, but I haven't thought enough about to say if this is necessary. But definitely, for our purposes, it's fine. So let's just assume it. Okay, so I'm not going to prove this because it's a bit involved, but it follows. I mean, some of the things are almost exactly the same, like the regularity theory is exactly the same. So there's some subtlety with the existence theory, and of course, this condition about vanishing at infinity is also highly non-trivial. So you should maybe think about it, but I think it would take too long to go through the details. So now the final part is we want to use this to prove this uniformization theorem, which I've been alluding to throughout the 2 weeks. Right, so then we have the following theorem, and this is the uniformization theorem. Right, so this generalizes the Riemann mapping theorem. So So the idea of the uniformization theorem is the following. So let X be a connected, well, simply connected. So simply connected for me means also connected, which is important up there too. Simply connected Riemann surface, then X is equivalent to either the Riemann sphere, this is the Riemann sphere. So this is the only compact example, which we've already essentially, we know how to prove using the methods, say by finding the meromorphic function. If it's non-compact, it's C, the complex plane, and it's D, or equivalently H, depending on your taste. So this is the unit disk. Okay, so just to remark like how one kind of distinguishes between these. Obviously, this is the only compact example, so it's already distinguished between them topologically. These two are topologically the same, but are not conformally the same, not holomorphically the same. And one way to see this is there are no non-constant bounded holomorphic functions here. On the other hand, there's lots of bounded holomorphic functions here. So that's the way to distinguish the two. So this is sometimes called the elliptic, the sort of elliptic parabolic and this is a hyperbolic which I think comes from kind of conic type sections. But, we'll see why this maybe makes sense in a second. So the corollary of this is then, right, we've classified now the simply connected Riemann surfaces, but I mean, you should convince yourself that if you're given any Riemann surface, you can pass to the universal cover, and that gives you a simply connected Riemann surface. And we already talked about taking these finite covers where you allowed branching, and there's some question about the relationship between the two. I mean, for example, whether the cover is regular, in other words, whether the deck transforms of the cover actually act transitively on the upstairs, so you can take a quotient and recover what you started with. So you should make sure that, of course, that in fact, when you take the universal cover, you pull back the Riemann surface structure in a natural way. The deck transforms are automorphisms, and the deck transforms act, it's a regular cover in the sense that if you quotient by the deck transforms, you recover your original surface. So that's something to check, but it's not too tricky. So the corollary of this is then that for any connected Riemann surface X, we have that either X is the Riemann sphere. So this is the elliptic case again. Either X is the complex plane, the punctured complex plane, or a torus. So this is, of course, a torus. Right, so again, this would be the parabolic case. And then the final situation is that essentially you have well, let's think of it as the hyperbolic space, the upper half plane. So it's the upper half plane mod gamma, where gamma is a discrete subgroup of PSL2R. So there's lots of such groups. This is a discrete subgroup. Which is acting freely, so the quotient is a Riemann surface. So some examples, there's lots of them, but for example, the punctured disk. The disk, the hyperbolic space itself, the punctured disk. What's another good example? The S2 minus 3 points, or any genus, any pot genus greater than 2 surface, oriented surface, Riemann surface. Okay, so this is somehow everything, most of the stuff is in this hyperbolic setting. And another important, I think for me, a more interesting, I mean, I'm more of a geometer. So one thing that this allows you to do is, of course, so this tells you that, I mean, remember, one thing to check is that a biholomorphic map, if you put a compatible metric on, I mean, if you choose a metric on the surface compatible with the Riemann surface structure in the way I've alluded to, then a biholomorphic map should be a sort of conformal map. I mean, if you have two metrics on them. So what this says is that any metric on the S2 is conformal to the round metric. Okay, I mean, up to multiplying by a constant. So if you normalize the volume correctly, you can put any metric is conformal to the, wait, sorry, that's silly. You don't need to normalize the volume, right? No. So any metric is conformal to a metric of, to the spherical metric, i.e. the metric of constant curvature 1 plus 1. This says that, of course, C, I mean, and C star is, of course, it's better to think of it as you can also think of this as a quotient of C mod the Z. So this tells you that on any torus you get a flat conformal to a flat metric, or on the punctured guy you're conformal to essentially a cylindrical metric, and then of course C you're conformal to the flat space. Right, and then finally this tells you that pretty much every other surface you're conformal to a constant negative curvature 1 metric. Right, so, well, let me I'm being a bit, it's a hyperbolic space. You have to do the following, which I'll leave as an exercise. So there exists a metric GH on H such that the whose isometries, and we know these guys act by isometries of the standard metric on C, but whose isometries are the conformal automorphisms, and and this metric G has a curvature -1, and so the point of all of this, I mean, this is something to check, but it's not hard. It's just the usual metric. Right. So this is GH. It's just in the standard sort of coordinates is dx squared plus dy squared over y squared, where we have h here is. This is y is equal to 0, right? So the corollary to this is then that so every, let me just say, every surface, connected surface X admits a metric G of constant curvature it's not necessarily unique. For example, like every surface, let's say every surface sigma, so every smooth surface. It's not unique, of course, because D star and C star have, not only do they have metric, it's a metric of type -1 or a metric of type 0, curvature 0, but of course also we have lots of different tori which get different non-equivalent metrics. And in fact, the point though is that these metrics essentially are unique in their conformal class, I think. It emits a complete, and this is an important, complete metric. Okay, and again, so the sign of the curvature is determined essentially by the topology or conformal structure if it's not compact. So if you look at closed surfaces where it's clearest, I mean, S2 gets a positive curvature, T2 gets a 0 curvature, and everybody else gets negative curvature. And so just a some remarks. I mean, there's an interesting thing, which of course you can prove this result directly by sort of PDE methods applied to studying how the curvature changes under conformal changes of the metric. What's interesting is in all this theory we did before is linear theory, whereas this is nonlinear theory. So it's, in a sense, harder for that reason. It's also, I mean, it's also kind of interesting, though, that in this case, in the nonlinear case, in the trying to do it with the Riemannian geometry point of view, I mean, remember the sphere was sort of the easiest. I mean, in a sense, it was the easiest part of our theorem. So in this case, it turns out proving the positive curvature case is the hardest. So that's a bit of a surprise. And I felt like I had one other thing to say. Oh, yeah. So I mean, the final thing is, of course, I mean, even if you're just interested in Riemann surfaces from the kind of complex point of view, this metric perspective does give you some interesting perspective, because, of course, you can now, I mean, you essentially can associate a unique metric to the Riemann surface, and you can try and understand sort of geometric properties of the metric. So, for instance, I mean, if it's a closed surface, you could look at its volume and see how that depends on the Riemann surface structure. You could also look at sort of the lengths of various canonical curves, like closed GD6 or something, and try and understand how that relates to the Riemann surface structure. A final thing is, even in the non-compact setting, I think this hyperbolic space it's illustrating to think of what is the complete metric on this guy look like. So it's supposed to be an annulus, and I mean, this is a very typical picture in this hyperbolic geometry. So it's an annulus that has sort of two ends, because it's an annulus, and so one end geometrically is enormous, like the volume grows enormously, like much faster than Euclidean space, whereas the other end is like totally negligible in some sense, where the sort of a length of a closed curve here is going to zero very, very rapidly. So this is sort of to contrast with the complete metric on C star, which is just a cylindrical metric, right? Where sort of, in a sense, both infinities have the same behavior, whereas here we have this vastly different behavior at infinity. And so again, in general, like how these, when you have a non-compact hyperbolic, surface that fits into this classification, what's going to happen is the sort of ends of the surface, at least, let's just assume it's somehow topologically a closed surface with a finite number of points removed. So in that sense, you should expect either the end to be kind of this cusp type behavior or this funnel type behavior. And it's interesting to sort of see which ones can arise. Okay, I'm going to move on now with the last 5 minutes and very, very, very quickly sketch the proof of this uniformization theorem. Okay, so let's try and prove of the uniformization theorem. Okay, so the key thing here is to find. So the step one is just like in the previous argument about is to use this sort of main analytic theory is to use the PDE theory to construct a meromorphic function Q that takes X to the Riemann sphere with a single simple pole P. And then the second observation is that actually the imaginary part of Q, which is a harmonic function, is away from the point P, that's supposed to go to 0. This is vanishes. It's supposed to vanishes at infinity. Okay? Right, so right, the basic idea, and I'll just sketch it, is to just do kind of what we tried to do the last time, which is sort of construct an approximate, an approximate guy. Which, say, Q hat, so this is going to be meromorphic near P, but that with simple pole, and then smooth and compactly supported. Away from P. In other words, it's supposed to kind of be a bump function, some kind of you multiply by a bump function to make it make sense away from P. And then the idea is to try and use the main theorem to kind of solve away the error. But one has to be a little careful here because, right, we use this sort of Dolbeault cohomology in the closed case to sort of argue about when we could solve away the error or not. But of course, we didn't have such a nice theorem about the behavior of the Dolbeault theory in a non-closed surface. And we obviously can't directly apply, you should convince yourself you can't directly apply the theorem to solve away the error, because then the theorem would give you something that vanishes at infinity in the real and the imaginary part, and that's probably too much to ask for. So what you have to do is, you have to be a little more careful, and you have to use the de Rham theory to sort of construct this cube. But maybe in the interest of time, since I have almost none, I won't do that. But you should think about how to. I think it's how to make this work. There's something that's slightly. It's a little more involved. Okay, but nevertheless, you get this meromorphic function, and then you want to use this meromorphic function to prove something about the Riemann surface X, right? So now you have this map Q from X to S2, and we have Q of P is equal to, Q inverse of infinity is equal to this point P. That's the only pole. And so the picture is we're supposed to have the Riemann sphere here. Here's, say, the point at infinity. Let's let this circle here, let's let this S1 be the imaginary axis, compactified with the point at infinity, right? So what we know, we know there's the P is mapping here, so there should be some neighborhood of this in the image, right? So if we consider the image of Q of X, we also know that as we go towards infinity, we have to go towards this, the imaginary axis. Sorry, this would be the real axis. Right, this is the real axis. So remember, so this is the points where the imaginary part component is 0. So the point is, as we go to sort of infinity in X, this assumption that the imaginary part vanishes at infinity means that we have to go towards this imaginary axis. But we don't know, we don't have to go through every point. We just have to go somewhere on the imaginary axis, or possibly near, even possibly to infinity. That would also be, not near infinity. Infinity is, of course, has lots of points, so infinity is sort of allowed in some sense. So the idea is now we remove this real axis, and we can look at sort of the H plus, the upper half space, and the H minus, the lower half space inside of Q. And so then what we can write X, we consider inside of H, we consider the pre-images of these upper and lower half spaces. Right, so these are open, the claim is that these guys are dense. So it's dense because the holomorphic map is always an open map, and the complement of H plus union H minus is this S1. So that means the set of points that get mapped to the S1 can't have interior. So that tells us that this is dense. So it's an open dense subset of X. And we now want to sort of use these X plus and X minuses to study Q. So let's look at Q plus minus, which is just the restriction of Q 2 plus minus. So Q plus minus takes Q restricted to X plus minus. So Q takes X plus minus to H plus minus. So the observation is, first of all, that these guys are these are proper. So the reason they're proper is if we take a compact subset of H plus, say, it has to be bounded away from the real axis. So it has to have a strict lower bound of the imaginary axis. And so that means that if we take the preimage under Q, by this fact that the imaginary part vanishes as we go out to infinity, that means that the preimage of our compact subset actually lives inside of a compact set of X. And since it's closed, that means it's compact, and so we have a proper map. So these are both proper, and hence they have degrees. Right? You can think of the degree of a proper map, and the claim is again the fact that the Q vanishes at infinity, and the fact that we have a proper map. I mean, a simple pole here, so it's sort of in a neighborhood of infinity. In a neighborhood of the pole on X, we map to infinity injectively. This actually is going to imply that these two facts imply, together with that properness fact, so this actually implies that Q plus minus have degree 1. So the way to see that is just to think about take points Pn and Qn either distinct, or if they're equal, then they're supposed to be with multiplicity 2, and just such that Q plus, say, of Pn is equal to Q plus of Qn is equal to I times n. So these points in the sphere are supposed to converge to the point at infinity, but at the same time, because the Q's they're very positive and imaginary, they're staying away from infinity in X, right? So that means that actually the Pn, you should argue that the Pn's converge to P, and the Qn's converge to P. And so if these guys are distinct, that violates the local injectivity. And if they're not distinct, then in fact the derivative had to be 0 at the point. I mean, you either can find distinct ones, or you can find a point where the Pn is if the degree is bigger than 1, right? Then either you have these distinct points, or you have a point where it's In and the derivative is 0. In either case, you violate the behavior at the pole, right? So then you get that the Q plus minus have degree 1. So then the final part is to put this all together, and then I'm out of time, but to imply, it's not, you should convince yourself, you imply yourself that actually Q taking X to S2 is injective. Right, so the fact that they have degree 1 means that the Q plus and the Q minus are actually biholomorphic maps. So it's just a question of when you put them together, do you get an injective map? But once you know that it's an injective map, right, once you know it's an injective map, then essentially the only thing that can happen is that that means the image is just S2 minus a compact subset minus I, where I is some compact of the real axis. Right, but then if this has more than one component, then this would say that the topology of X was not simply connected. And so this has one component, so it's either a point, in which case you have a biholomorphic map to C, or it's an interval with non-empty interior, and then you have to convince yourself that you can make that equivalent to the upper half space by some choice. I mean, there's an explicit choice of holomorphic map that does that. And that concludes the proof with a huge amount of rushing. So I'll stop here because we're all hungry.